Okay, last class, we talked about multiplication. This was a combinational multiplier. Combinational multipliers are bad because they are why are combinational multipliers bad? Yes?
Like really large.
Sure,
Slow?
they're pretty large. They're extremely slow. That is the problem with them. So actually, I guess they run pretty quick. The issue is that if you were to have a flip-flop on either side, if you were to feed the inputs with a flip-flop and then read the output with a flip-flop, you would have to run at a very slow clock frequency in order for there not to be any like setup violations. Okay, so how do we fix this? How do we make this run at a higher clock frequency without there being any timing violations? What do we do? Okay, yes?
I guess maybe this is spoiling it a little bit because I did this over the weekend.
Yeah, no, perfect, yeah.
You could store the previous, instead of having like a for loop, you could have a counter that counts how many times you iterate over the combination of block.
Perfect, okay. So absolutely, yeah. So maybe we can have like an internal register that will perform maybe like incremental calculations, right? And so you now can split out the multiplication calculation over several clock cycles. And yeah, so maybe you actually run a little bit slower, but now you run, yeah, maybe now you can run at like a whole gigahertz now because maybe you only have like a single mux and a single addition that you do per cycle. Okay, so let's see how we can do this. So as Li Wei said, so we can probably just remove this for loop right here, and we could maybe replace it with a counter. Okay, so hopefully you are super experienced and practiced at writing up counters at this point. So the way you do it is you say logic, and then we can, I guess our counter can just be like width. Maybe we would want to make it like C log width. Oh yeah, question. Yeah.
Is it okay to have a combinational adder if you just have like flip-flops at the end, or is it just like not?
A combinational multiplier?
Or a combinational multiplier if you have like flip-flops at the end and then you just have it work that way, or?
So yeah, the issue with that is oftentimes it will not work. If it does work for you, then yeah, that's good. Most of the time though, if you use this design, you will get timing errors all over your tool. Your tool will say, sorry, I cannot like do anything with this. You must either change your design or you must slow down your clock frequency. And oftentimes you don't want to slow down your clock frequency because it'll slow other parts of your design down. Yeah, okay. So let's quickly make our counter. So we'll just make it, I don't know, width bits. So we'll call this maybe count D, count Q. Okay, and then always FF. Pause edge. Okay, pause edge. Well, so we're probably going to need to change our ports here, right? So what do we add to our port list? What was that? Not quite. We're not there yet. We're just making the counter first. Clock and reset. Cool. So input logic. So we'll do clock and reset RST I. I'm going to leave off the underscore I for clock for digital JS reasons. Okay. So now we can do pause edge clock. And if reset, then count Q, we can just by default set it equal to 0 and else begin. And then count Q is now equal to count D. Good. So now we need to assign count D. And count D can probably just be assigned maybe within this always com block. So, and I will also move these signals higher because I think some tools will get mad at you. I think Icarus will get mad at you if you don't declare these first. So I'm going to declare these first. But great, now these represent the D input and Q output of a flip-flop. So now we can go. So I'm going to now remove this for loop. Okay. Well, actually, maybe for a second. So yeah, okay. Maybe discuss with the person next to you. What do we do here? How do we change this from just being a for loop to using the counter and maybe just assume that after like some number of cycles, the data will be valid, and we will figure out how to deduce when data is considered valid later. But like for now, let's just see like, can we get any sort of output? Okay, go and discuss for like a minute. Any ideas? Okay, yes.
What I would do is I would have count D, like determine how many times I've added A
Okay,
to my output.
sure.
And once count D is at BI, I would like somehow say that, oh, my data is like good to go.
Okay, sure. Let me show you what I was thinking. I think we're on kind of the same idea. So the first thing is, so by default, like in our counter, we want y out to be equal to 0. So I'm going to say, like, assume that maybe we have just hit a reset, and then like on the next cycle, maybe A and B are valid or something. So okay, A and B are now valid. So that means that if we are on cycle 1, so if count Q equals 0, then maybe we can just say like y out equals 0. Then we can say, well, we can look at the value of b of I, and we now can check this counter value. And so we say like, if b of I, or if I guess b of count is set, then we need to go and add in that value, but we need to then shift it. So then, good, okay, so then we shift it, and then now we can add it to y out. But instead of y out, right, so we want to keep track of this over multiple clock cycles. So maybe we need to add another flip-flop that maybe is like product. And so maybe instead of just y out, maybe this is like product D. And then also maybe by default, we can say product D is equal to product Q. Okay, so let's walk through an example. So, okay, let's say we are on like the 3rd clock cycle. So count would equal probably maybe 2 here. So count equals 2. But then what we do is we grab the value, the previous value of product, and then we check, well, is count equal to 0? Because if it's equal to 0, that means that we've just received like a new value. So now we need to go and clear out the previous product. But in this case, count equals 2. So therefore, we're not going to clear out the previous product value. Then what we do is we check B of 2. We see like, is the tooth bit of B set? If so, go and increment our product to the new value. And that looks like that will properly deduce the value for the next state. It looks like it will, in fact, create the next value, the correct product output for product. I guess now the question is like, when do we stop? And also in a way, like, how do we start? Like here, I guess I'm just assuming that like after we hit reset, that count will just start counting up, and that will be good. So there's a little bit more plumbing that we need to do, but okay. Yeah, question, Albert.
Can you explain the product D plus equals AI, like, shifted by count D one more time?
Yeah, so the point of this, so product D is like the incrementer, like it's the thing that is storing our intermediate sums that go into a multiplication.
And then if whatever bit that count D is referring to is 1,
Yes.
we're gonna add AI. Why are we like shifting? Like, why are we adding AI
Yeah.
shifted by count?
Yeah, good question. So, oh, is it working? There we go. Okay. Can I? So if we go back to like this example, so in this, we're assuming that we're multiplying like this 4-bit A by this 4-bit B. And if, let's say, for example, like if b of 2 is 1, then in order to properly handle it, we would want to add this value, but shifted by like 2 spots. And that's like, that's to just take into account just like the general multiplication algorithm. Like the idea that when you have like a number in like the 0th place and you multiply it, or I guess the ones place, and you multiply it by this number, then you just perform this multiplication like normal. But when you multiply it by something like the tens place, then you would have to shift this. Yeah.
Okay.
Yeah.
Okay, thank you.
Yeah. Cool. Okay. Yeah. Very good. Okay. So in theory, this should work. So let's go and test this out.
Never set product Q.
You are correct. Thank you. Oops. Product Q. Just filling out the always FF block. And then we can also go and set y, we can do assign y is equal to product Q. Okay, let's see what happens. Okay, yeah, it's going to be fairly big, but okay, let's go in, it's kind of small. Let's do 2 multiplied by 3. So what we should see is, I think it'll be broken, but then as soon as I now go and reset it, we should see, so you can barely see it, it says 0 right here. So it's being reset to 0, but now we should see that it will eventually like reach the value 6. Okay, so I'm going to let go of reset. And now it says X, oh shoot, okay, something weird is happening. Okay. Oh, we are not setting count D anywhere yet. So let's just go and set count D. We can do count D++, and then we can also say count Q, or actually, let's just do count D is equal to count Q plus 1. Count Q, oh, count D. This needs to be count D, yeah, okay. Let's see. Maybe it's a width issue.
Why is it?
Yeah.
Yeah, isn't product shouldn't be the same as width of the output Y? The output Y is-
That shouldn't, I don't think that will change anything, but yes, it should. I can do 2 times this. Okay, okay.
Can you read from count D inside of the alt? Should we count Q instead?
Oh, wait, what the heck? Why did I do that? I think that's totally it. Yeah, you should only ever read from from Q. Yeah, thank you. I don't know. Oh, now I'm taking a screenshot. Does that work? Did anyone test it? Okay. All right, 6. Okay, well, there we go. It looks like it worked that time. Great, okay, fantastic. So now it works. I don't know if you noticed that though. Here, I can hit reset one more time though. So you can see, actually I'll multiply it in the other direction. So make this be 3 and I'll make this be 2. So if I zoom in on here, so you can see it becomes 2, and then it becomes 6, and then it becomes unknown. And the reason for that, right, is because we keep incrementing count, but we don't want to keep incrementing count. We want to stop calculating things once we have finished the calculation. Okay, so in that case, what we need to do is we need to put something that signifies like, hey, we are done calculating this. And probably another thing that would be useful is some sort of input signal that says, hey, A and B, these now are like valid signals for us to deal with. So this goes into kind of the next kind of most important learning outcome of this course is a very common interface called a ready valid interface. And if you've taken CSE100 with me, I briefly talked about it, but we're going to be spending a lot more time on ready valid in this class versus in CSE 100. So ready valid. I'll mention, so ready valid interfaces are used in almost any parallel, like on-chip communication interface. There is like Axie and Avalon and Wishbone. And there are several, protocols with like very large documentation PDFs that are effectively just, when you boil it down to like what it is at its core, all it is just ready valid. And we can add a ready valid interface if as with the following. So we can say, like, assume that A and B are actually only valid inputs, or like we're ready to receive A and B, only when this additional net right here also goes high. So when valid I goes high, that means that every other input is also going high. And if I want, I can call this like operands, or I can call it like invalid. And then similarly, when we are done calculating everything, then we can go and add an output logic, and call this like out valid out. Okay, we'll come back to ready in a second. Okay, I don't know why.
You typed out backwards.
Thank you. I meant to do out. Thank you. Good. Cool. So let's go and now handle this properly. So maybe what we can do is say, maybe on this, maybe we can add just like a big if statement that says like if count Q maybe is equal to width. Okay, so if count Q is equal to width, that means that we are done. So in that case, we can say that like out valid is equal to 1, and that's it. But if count Q is not equal to 1, then go and do all of this stuff. And also notice that we're going to need some default values for this. So I will go and pull this out. There we go. And maybe out valid by default should be equal to 0. So out valid is only true once the width has reached, once count has reached width. Okay, let's now also do something similar for invalid. So now, the question is, how do we modify this to now handle invalid, to where we only consider, like we only begin the operation once invalid is high? Okay, look at this for a second, think about it. Okay, Ollie?
You could use, instead of doing if just reset, you could do if, or no. In the flip-flop, you can basically check for the validity of the input every time and only start working if it is valid.
Sure, right. So instead of like if reset, you could have something like if reset or if like invalid or something.
Or yeah, something like that.
Yeah, you could do that, but actually that, like the always F block, always FF block, the only thing that should ever go inside of this is just like if reset. Like you don't want to have any like extra kind of logic and gates and things in here. So we definitely want to keep it in our always comp, but yeah, it's going to be similar to that. I was
gonna say once like our count is equal to the length of PI, but I also have a question. Wouldn't that just make it so that like you only have output for like one cycle and then like it's, or like okay, like, because technically the computation is done once we get through all of like all of the like bits of whatever thing we're multiplying by.
Yes.
Right?
Uh-huh.
So
I think this will do it, right? Because once the count reaches the end, then it will no longer increment. So it's going to be just stuck at count Q is going to be equal to width.
is there like any expectation that we leave it like that for a bit, or like?
There's no expectation yet.
Then can you set ready to like 1 there, once it equals with?
So we're not dealing with ready quite yet. We're just looking at invalid. But so one thing when I'm looking at this is it's like, yeah, it is a little bit tricky to think about, like, to keep in mind like all of the different possible states. It's like, okay, when Q is equal to width, and like, okay, well, if count Q equals 0, like keeping track of all of these kind of if statements, it's a little bit tricky. What I like to do is to model this as a state machine where I have discrete states. And this will end up simplifying things a little bit to where it's a little bit easier to understand. So I'm now going to make a type def enum. We'll do logic. And it may be like just very simple. State T. And so first what we will do is maybe we'll have an idle state. Maybe idle is before we actually receive the invalid. Okay. Then maybe after that, then once we've received invalid, then we are going to be in a working state. Then after we have received, like once we've calculated the final value, maybe after that, then we have like a done state. And then once we have properly sent out like this data, then maybe we go and reset back to idle. Okay, so let's go and do that now. So we can do, we could do cases, or we could just keep doing if statements. So I'll say if, and let's also make some state values. So state D, state Q. Okay, state Q, oops, that's fine. Okay, by default, reset to idle. We don't want to set it to a constant, like a 0 or anything. We want to set it to an actual state name. Okay, good. And let's go and set state D inside of our always comp. So we can say state D is equal to, by default, just make it the previous state, so state Q. Then we can say if the current state is equal to idle, the question is like in what condition do we move on to the working state? Okay, yes.
When we get our input invalid.
Exactly, yeah. So when invalid, then in this case, then what will happen is we should probably go and actually reset count down to 0. Okay, so so count is going to be reset. Then we go and set the next state to working. Okay, so next state will become working. And I think that is good. That's all we need to do if we are in the idle state. Then if we, oh yes, question.
Do we not need to reset product,
Oh, you know what? Let's do that as well. Yeah, I think you're totally right. Yeah. So let's go and reset product. Thank you. And now we can go and else if. Now we can do state Q is equal to working. So yeah, while we are working, this will be pretty much just this right here. So while we are working, we want to go and increment the count. We also want to probably get rid of this. We can say if count is equal to 0. Yeah, actually, so we can remove this because we are already doing that up here. Okay. And now all we have to do is just, leave I, just this standard thing. But now we need to figure out if we are done. So how do we know whether we are done? Okay, yes.
if our count Q is equal to our width?
Yeah, that's what I'm thinking. So we can say if count Q is equal to width. Actually, it might be width minus 1 because we're like saying like if we are about to be done, like if we are currently processing the last element, which will be element width minus 1. So if we are currently processing the last element, then on the next cycle, go and set state D equal to done. Okay, and then finally we do else if state Q equals done. And if we are currently done, then out valid will be equal to 1. And well, at this point, if we wanted to just have out valid be equal to 1 for just like one single cycle, then in that case, we could probably just go and set, so let's say, so one cycle, then state D would equal idle. If we wanted it to last longer, then we could add like an extra counter or something in here. Okay, let's go and check this. Hopefully this works. Okay. 22. Anyone see the issue?
Because you mentioned state Q before defining it.
I think so. Okay. Cool. So things are a little bit more complicated, but honestly, that's fine. If you look, it shouldn't actually be. I think it's just. Oh, it's not working. Oh, let me zoom out. That's okay. All right. Things are a little bit more complicated, but I think you'll find that it won't actually run too much slower now that we've just added that control logic. Let me go and hit reset. And let me go and set A to 2, B to 3. And now even if I let go of reset, we should see that Y out, you can see if you squint, that says 0. So even though we have disabled reset, this is continually held at 0. But now if I go and say like, hey, we've just received a valid input, then it's going to start counting up. So good, now it says 2. And then now it says 6, and then we should see out valid becomes activated. But it was only activated for just one single cycle. And it's actually now looping over and over because we're saying like this input is always valid. So now it's always going to just be like receiving in the next data, immediately processing it.
So
Okay.
out valid is like, at least in this implementation.
Yep.
It'll cycle between like on and off, basically.
Well, it's because when it is valid, we are making it intentionally only be high for one single cycle.
Mm-hmm.
Yeah. And then immediately it will receive more data. But if we go and now turn off like invalid, so if now it is no longer going to receive an invalid, it's no longer going to receive a valid signal, then you can see it goes high, but it'll just stay off indefinitely after this, and it won't turn back on because we're not saying that we are passing in another like valid signal. So this will stay off until I go and send in another like set of operands. So when I set like, hey, the data is valid again, then we go and look at it. It'll take a second. Okay, 2 and 6. And then there we go. Now the data becomes valid.
I guess I'm confused by like the name of invalid high.
Okay.
Because wouldn't in mean it's not?
Oh, sorry.
valid?
This means the input is valid.
Oh, okay. I see.
Okay, yeah, thank you. As opposed to the output is valid over here. Out valid.
Gotcha.
Yeah. Okay. But potentially an issue with this, though, is so here we're making the out valid signal go high for just one single cycle. But that may not be fast enough for us to process it. it's possible that maybe the like consumer of this data, maybe the consumer of this product is going to require like some amount of like setup time, like some number of cycles in order for it to like, before it can actually process it. So what a better thing to do is to have a ready signal. So a ready signal will be like, if I have like an output ready, this would be fed out of the consumer of this data. Like for example, if you have maybe like an adder after this multiplier. So maybe you perform the multiply, then you go and pass it into an adder. Well, if the adder is not ready to receive the data, then it will send a 0 out on the ready signal. It's like, hey, I'm not ready to receive the data. And in that case, the multiplier can pause for a little bit. It can pause, it can say like, hey, I'm valid. I understand you're not ready. I'll just kind of stay valid for a little bit until you are eventually ready. And then once the adder becomes ready, then it knows, okay, the adder was ready and I'm valid. That means that since we are both ready and valid at the same time, then that means that the adder has successfully like sniffed the data and has received it. Now I no longer need to keep my data valid anymore. Now I can go and reset back to idle. Okay, I'll show you what the code looks like. So we will go and add a out ready signal here. So out ready, and actually this is an input, right? So if we were to receive this ready signal, it's telling us like, is something ready to receive this output? Okay, so we have out ready as an input. And now on done, we can just say if out ready. So if someone is ready to receive this data, then go and on the next cycle, move to idle. But if someone is not ready to receive the data, then just stay inside of done and like wait there until someone finally is ready to receive this data. So if I go and synthesize this, so okay, I will do once again I'll just shorten it. Okay, good, reset. So now I've reset, and I'll say, so I will say, yeah, okay, so let's say out ready is not true. So just by default, I am not going to be receiving any data. But if I now say, hey, the data that was just put on A and B is valid, then we should see after a second that boom, okay, becomes high. So it has successfully produced the product, but the data is staying valid because it knows like, hey, the adder is not yet ready to receive this data. And so this is going to stay green until eventually, I guess it's too small. Eventually when someone goes and clicks this checkbox right here, this out to ready. So when the receiver is ready to receive this data, then it will reset back to idle, and then it will, it will no longer be valid. So I will show you that. So, okay, where's the clock? Okay, so I will hit out ready. There you go, you can see it's green, and then boom, change to red. There we go. So data transfer, in theory, has occurred. Yeah. Oh.
Can you like draw out how like two interfaces do like red and valid on like your iPad if that's possible?
Yeah, absolutely. Yeah, I'll do that. Okay, so order of operations. So we'll say that the producer is the multiplier, and let's say that the consumer is an adder. So the first thing that happens is actually on like the other ports, maybe like the user sends A and B and valid. to mult. So this is the first thing that happens.
Is that valid I?
This is valid I, thank you. Yep. And then step 2, now the mult will work. And then finally, mult will produce product and valid out. And if I draw this out, so if we have mult here, so if this is the user, so if this is A, and then this is B, and then this is valid I, and then the multiplier will produce product and valid out. And the adder will produce ready. And all of these names here are relative to the multiplier. So if we were to implement the adder, we would actually see that valid O would actually be valid I, because it's an input to the adder, and then ready I would actually be ready O, because it's out of the adder. Yeah, Leeway.
Why does the adder produce ready I?
Because the adder, that's just how it works. The adder will tell the multiplier if it's ready to receive this signal. If it's ready to receive the signal, then the multiplier will know that, if the adder is ready to receive the signal and the multiplier is sending out valid data at the same time. So if ready is being sent and if ready is being sent and valid is being sent, then we know that they're both able to receive data. They're both happy to have data flow occur. So then in that case, multiplier will then switch back to the idle state on the next cycle because it knows that the adder has properly received valid data.
And adder is like the counter that we implemented earlier?
No, adder would be some sort of external module. Maybe this is maybe you just have a bunch of modules all connected with the ready valid interfaces. The counter is embedded in here.
Right, okay.
But then what's the point of the adder? If we already have one inside doing the product.
Oh, maybe this so we have a counter on the inside. This counter just helps perform the multiplication, but maybe this will be fed into some maybe it takes in a lot of other things as well. And maybe
it's one of those things
it's
with
not
a GPU that multiplies and then adds.
Yeah, maybe
a bunch of these.
right. Maybe it takes in the multiplication and then it performs some kind of complicated other adder. I don't know. Maybe this just in this example it needs to be a separate module. I don't know. You just have ready valid interfaces where you have a module producing a ready valid interface and then a module taking in a ready valid interface and then communicating over that. Yeah, Albert.
Does everything would the multiplier also need a ready input?
Wait, great point. So what if the user, okay, hold on. Before I move on to that, is this making enough sense? But yeah, anyway.
So I guess, just to confirm, let's say so you said the user sends A, B, and valid I.
Mm-hmm.
And then once the multiplier receives that, then it does the multiplication.
Yes.
Then it will produce the product and the valid O.
Yes.
And once an external circuit, the same adder,
Yep.
receives receives the product and valid O, it'll return ready I.
Very close. So the adder can just return ready I anytime it's ready. If it can just hard code it to 1 just all the time. It can just always be ready to take in data. But data flow will only occur if both valid and ready are like if both of them are high. Yeah. So
Okay.
adder will produce ready or has been. Or has been producing ready. So the adder could have been ready for like a long time, or it could have waited after the multiplier had a valid output. It could like have seen that and then waited a couple cycles, then gone and produced ready. And so data flow will occur if ready and valid are high. Yeah.
In an ideal scenario, this should take like one cycle. Like the first one should be 2 cycles. Afterwards, it should be 1 cycle if it's like ready instantaneously.
Yeah, I would say, yeah, exactly. The shortest amount of time is it must take at least one cycle. Yeah. Yeah.
When, like, in the multiply stuff, when we did the states.
Yes.
When, like, because right now, from my understanding, will always just be, like, the product is valid. So, like, when does it, so does it switch to, like, doing work again as soon as you get valid again, or?
Correct.
Okay.
Yeah. Right. When you, so I guess kind of an important purpose of this is if you receive a valid input, actually, hold on. No, I won't go there yet. Okay.
Like,
Wait, I forget. Wait, so tell me the question one more time.
Like, okay, so say user produces a valid input.
Yeah.
But our multiplier isn't done.
Okay,
and,
sure.
Like, what happens then?
Yeah, so there was a great question that moves me into the next part. So if now the multiplier, let's say the multiplier is like currently in the process of doing something and it receives another valid input. In that case, it seems like the multiplier was not actually ready to receive user input. So therefore, we're actually missing a signal here. What is the signal that we are missing on this side? We need actually a ready signal. There needs to be some way that we inform the user. We need to like tell the user, like, hey, we are not yet ready, or like, yes, we are ready. So this is now ready out. So the multiplier will tell the user like if it's ready to receive data. So this is the final piece of the puzzle here. So let's,
Going back a little bit, I guess when you said like, what was it? When ready and valid are 1.
yes,
Is it ready I and valid O?
exactly, yeah,
Okay.
right.
Gotcha.
Okay, so let's go and now do this last port. So notice we have out ready here. Well, it's going to be very similar here. So we just have out, sorry, what am I saying? In, this is going to be in ready out. In other words, like, are we ready to receive input? So this is an output. So we are telling like, yeah, the user whether we are ready to receive data. So now we can go and assign this and we can assign it here. Maybe by default, we are not ready. So the question to you now is, when are we ready to receive user input?
When idle.
When you're idle.
Exactly, yeah, when we are idle. Perfect. So when we are idle, it's now equals 1. Okay, yeah. Oh,
When do we go from, okay, so when we say out, sorry, When do we go from done to valid? Can you, when do we go from done to idle?
To idle,
Yeah.
we go from done to idle when when we're in the done state, and the output, like if the thing we are outputting to, like for example, like the adder, if the adder is ready to receive our valid data.
Okay, so we only do it like, so for one cycle?
For one cycle.
Thing, and then we go back to being idle.
Exactly. Yeah. It could be more than one cycle if our output port is not yet ready to receive our valid data.
Okay. But like once they're both high, it takes one cycle and it's reset.
Exactly. That's exactly right. Yep. And most likely the adder will like be sniffing sniffing this port. Then finally, when it's like when both the data is valid and it is ready, then it's going to take in that data and start processing it. And that ready signal will now drop to 0 because it's no longer ready to receive more data because now the adder is processing the data. Cool. Okay. Ready valid. This will be in every single one of your labs moving forward, probably almost in like every single part of every single one of your labs. So if you have any questions on this, let me know. But also, you are going to be getting so much experience with this throughout the quarter. So it's not the biggest deal if you're not an expert yet.
Can you scroll
Yeah.
up a little bit?
Yeah. You can also zoom out here to the ports.
I think I know the issue.
And so now this is a sequential multiplier. This is much better. Okay. I want to pull up a quick practice question that I will leave you with. I think I will say, so I posted a couple practice questions on always com blocks on Canvas. You're welcome to go through those. There is a final exam at the end of this quarter, and there's a good chance that asking you to like hand draw the circuit for an always com block, that's a very reasonable question on final exam. So I recommend going through at some point, going through those practice problems. I will probably also put a couple practice problems relating to ready valid. So feel free to watch out for those. I'm now going to pull up something. Okay.
Does your circuit compile?
It does.
Oh.
Yeah, and I can share this code. Of course, on your homework, you will need to implement a Booth multiplier. So you can look on Wikipedia and online how to do that. The most important thing is just getting practice with the implementation techniques and doing ready valid interfaces and idle working things. Okay, this is fine.
Could you scroll down a little bit?
Oh.
Or unless you were switching into.
I'm going to switch. Yeah, Ella?
On the, or at least on this homework, is already to like jump around between parts.
Yeah. Yeah, definitely.
For some reason, like.
Oh, yeah?
I'm getting like.
We-
Assigning to input. Maybe I can talk to you after class.
If you're assigning to an input, then maybe you forgot to change it from an input to an output or something in the port list. Yeah. Okay. I want to quickly show you this. So on this homework question for my CSE 100 class, maybe you guys remember this if you took it. So the question was, you were given this circuit, which is honestly very similar to the one that we just implemented, where we just have like idle, working, and done. And we have like if consumer ready, then go and reset. If producer valid, in other words, like this would be like the user valid, and this would be like the adder ready. Then in that case, then go and like transition to the next state. So this should be like pretty like similar to what we just did. Okay. The question now is finish the waveform. So you're given that by default, we start in idle. And so the question, I guess, is what is the, what happens on maybe this first clock cycle? And so this is reset, so I guess this will stay idle as well. Okay, but what happens starting here? So the producer valid was high. So that means that instead of idle, what is the new state that we have transitioned to? Working, okay. So this becomes working. Good. Working will only last, actually, this should be working, okay. And then this now transitions to working. Good. And now we are in this state. What state is this? We can ignore D actually. Okay, so what is the next state? So working, that's okay. So working lasted only one cycle, it looks like. So immediately, as soon as we're in working, we immediately transition to done. So good, so we can put done. Then afterwards, what is the next state?
Idle.
So the next state is actually going to stay done.
Oh, until it reads it.
Exactly, yeah, because there's like a 1 cycle delay here. So now, finally, the consumer is ready. And at the same time, right, the data is also going to be valid because the data is valid when we are in done. So data is valid and data flow occurs right here. And so now on the next cycle, now this becomes idle. And this is going to drop low. Okay, let's just finish this out in the last minute of class. So what will the next cycle be?
Working.
So if we look at the previous value, we can see that the producer was not yet ready. So it's still idle. Yep. And then now, finally, we perceive that the producer is valid. So now on the next cycle, we are in working. Okay, and then now we can see that we receive this ready signal. So what happens next?
Done.
Okay, done. Okay, well, we had this ready signal, but actually this was from a cycle ago. So what is the next clock cycle? What's this going to be? I think this is still going to be done because we never had the case where we were done and ready happened at the same time. Yeah, I will say though that we are at least, this is a value of 1 here. So okay, so good. So now this is going to stay done. And once again, this will stay done. But now this goes high. So finally, this next cycle goes to idle, right? Good, okay. And if we finish drawing this out, this goes like that, okay. And then next clock cycle, what happens here? Were we in the idle state at the same time that a producer valid was true? Yes, we were. So therefore, this will transition to working. And then on the next clock cycle, we are done. Yeah. Okay. And then finally, let's quickly do the producer ready. So when are we going to be ready?
When done.
Not when done. Producer ready. Let's check this. So producer ready is true. When idle, yes. So okay, so it looks like it will be probably like 1 here until like there, and then to like there, I, and then all the way until I. There we go. And notice that data flow occurs like right here when we have ready and valid. Data flow occurs here when we have ready and valid. Data flow occurs here when we have ready and valid. Here, oh, actually, no, not there. right? But then data flow does occur here, and it does occur here, and right here. So yeah, each one of these are a ready valid like transaction. This is the producer port, also known as like the in port, and then this is the consumer port, also known as the out port.
Just to confirm,
Okay.
what do you mean by,
Yeah.
by data flow?
Data flow means that you're welcome to leave if you need to head out. Data flow means that the listener, like the receiver of the data, is going to take in that data, and the producer of that data is aware that the consumer is receiving that data. So
So the data was written to like the data lines, but it wasn't actually pulled into the circuit until data flow happens.
exactly.
Okay.
Right. The data will be like put on the bus, but yeah, it will assume that no one actually received that data until both like ready and valid are both
So
true.
it's like putting something in the top of a copier, but it doesn't actually happen until you press the copy button.
Sure, absolutely. Yeah.
That's a good analogy.
Yeah, Marco.
Could you upload this here also as practice with them?
Yes, I actually will. I will upload this. Yep. Yeah. Albert.
Do you have time to check off today?
I can do a couple checkoffs. Yeah, but we'll probably take it outside. Okay. Thank you, everyone. I will see you on Wednesday. We will talk more about Ready Valid.